Hello, this is Dr. Christy Lukes for Thermodynamics 1 for Chemical Engineers. And in this video lesson, we're going to be looking at some very straightforward examples of using definitions of heat capacity, both C sub P and C sub V. So in this first example, we're going to find the change in internal energy when graphite is heated from 31 degrees C to 78 degrees C. Now, the change in internal energy is, by definition, C sub V dt integrated, or C sub V delta T if C sub B is constant. And in this case, they told us that C sub P is 0.61. So that's close to what we want, but delta U is C sub V delta T. But graphite is a solid. And for solids, C sub P and C sub V are about equal to each other. Therefore, we can simply calculate delta U as 0.61 kilojoules per kilogram Kelvin times delta T, which is 78 minus 31 degrees C. Fortunately, in delta T, degrees C and degrees Kelvin are the same, and so therefore our answer is 28.7 kilojoules per kilogram. Okay, and this is again delta T in degrees C equals delta T in Kelvin. In this next example, we're going to look at the enthalpy change of CO2 being cooled from 1200 Kelvin to 200 Kelvin. So this is a large temperature change. And if you look at the data for actual measurements, the delta H for this is negative 1088.1 kilojoules per kilogram. Now, if you look up online a constant value of C sub P, the value that I found was 0.842 kilojoules per kilogram K. Delta H is, by definition, C sub P delta T for constant C sub P, and so therefore it's 0.842 kilojoules per kilogram Kelvin times 200 Kelvin minus 1200 Kelvin, final minus initial. And so therefore negative 842 kilojoules per kilogram. Now this isn't very close, right? And the reason is that this value of C sub P was at approximately 300 Kelvin. And although we go through that temperature, the temperature range is very wide. And for gases, it's going to be really hard to find a constant value of C sub P that's very good. So a constant C sub P is bad for gases. I mean, occasionally you may get lucky and get the right one that gets you a good answer, but generally it's bad. It's considered okay for liquids if delta T is not too large, but generally it's not too far off as long as it's liquid throughout the entire process. And usually it's considered to be pretty good for solids. But for gases, constant C sub P is a bad idea. So what are we going to do? Well, let's look at this next example. All right, so let's look at this next example here. And this time we have a function of temperature for C sub P. So in this case, C sub P is this polynomial expression of theta, where theta is T over 1000. And the way that you use this